So, greetings. Let's just recap where we are. So, the aim of this video today, within this video, is two things. First, that function TP is continuous. And the second thing we want to show is that the poset 2 to the z is a CPO, complete partial order. Why? Because from these two things, applying the Tarski Fixed Point Theorem, we can deduce that there exists. So, deduce that there exists a least prefixed point, which happens to be also a fixed point, so least prefixed point of TP, which can be computed by iterating the TP function from the constant zero assignment and then just taking the limit, the supremum of this iteration sequence. So, which is the TP function applied n times on the constant zero assignment, and just take the supremum of these things. And because 2 to the z is a CPO, the supremum will exist. And because the TP is a continuous function, the fixed point can be computed this one. And this least fixed point is, this has to be, will be the so-called canonical semantics. Canonical semantics of the logic program P. Program P. So basically our aim for defining the semantics, the correct semantics for logic programs will be solved by this step, because we want to have a model of a program. We know that a model is a prefixed point of TP. We want a minimal model, so we need a minimal prefixed point, and this theorem says that there is exactly one minimal prefixed point of TP, which is the least prefixed point, so we have no other option there if we actually manage to show these two things. Okay, let's do this. So first, let's just recall what the function TP is. So TP is a function which gets an assignment and outputs an assignment. And the output, so the new assignment, is defined as follows. For a variable q, we should just collect all the clauses having q at their heads, or as their heads if you prefer, in the program P. Evaluate these guys, so according to the old assignment up1 and so on, upn, and then take the supremum of these values. Now this supremum is always well defined because this body evaluation gives you either 0 or 1, so this is just the supremum in the poset 2, which is a poset in which all the possible suprema exist. So the supremum is always well defined, which means that TPU is always well defined, even if you have an infinite number of variables or an infinite number of clauses, which might happen if you originally started from a first order program, just in the first video about logic programs, there was a method how to produce, in theory, an infinite propositional program from, say, a finite first order program. Cool. Now, so this function, the continuity of this function is built up from smaller and smaller steps chained together. So at the very first thing, so u is the input, and we compute this very complicated thing from u. But the most basic building blocks of such expressions are these guys. Just evaluating one single variable, you get the function u, and just evaluate the one specific variable. Now this is what's called a projection. So it's just like a definition, and we will prove that these projections are continuous, and there is a conjunction of projections. We will prove that a finite conjunction is always. So just putting such a finite conjunction is also a continuous function, and taking the supremum for these options is also a continuous function, and so on. So we will just build larger and larger functions and show them this is continuous, and so this is continuous as well, and this is continuous as well, and at the end, as the end result, we will get that this TP function as a whole is also a continuous function. So that's the progress we will make. So the very first basic building block is a projection. So basically, what do we have here is when say we have P is a poset, I is some index set, like for example here we will index by the variables. So in the case of logic programs, Z denotes the Z is I, so the Z is the index set. I is an index set, is an index set, and I just pick one particular index. Then say P, usually this Greek letter P, I, denotes projections. That's why I'm using these notations. Pi is just projection onto the ith coordinate. Basically, you can think as an operator which gets an array or vector of values and just outputs the value on the one specific coordinate on that vector, right? So then Pi will get, well, not a vector but a function. That's almost the same for me. So it's P to the I to P, right? So it gets a function and outputs a single value from the P. And how? So Pi, the ith projection of a function or a vector of u, should be just the value of u on the ith coordinate, is called, and I'm just using range as usual for definitions, is a projection. So projections are just simply evaluating functions at a fixed point, so it's just a mapping, okay? Now we have that, let's say statement, projections are continuous. Okay, so this is statement, and I will prove this. So a projection is a function which gets a number of functions and outputs So a projection just gets a function and outputs a value from the range of the function. So projections are continuous. Proof. Okay. So let's say for being continuous, I should just start from a subset of p to the I, from a chain having a supremum, and prove that the function application operator and the supremum operator can be solved. So let's say f be a subset of p to the I, and in the continuity definition be it's a non-empty chain of functions. It's a non-empty chain of functions, meaning if there are two functions f and g in this capital F, then either f is smaller than or equal to g or g is smaller than or equal to f, right? So that's what makes it a chain of functions. And let f star be the supremum of this set of functions. Okay, we have to prove that for continuity, for the definition of continuity, I have to prove that the function whose continuity is to be shown is the ith projection. So if I apply the projection to the suprema of these functions, is the same as just applying the projection on each element of the input set, okay, and just take the supreme of the resulting set. In the left hand side, this is just f star in the supremum of f construct, which is a supremum of functions, and on the right hand side there are values which are in the poset p. Okay, so by definition, what's this? Pi of f. Pi of f, if you just check the definition, pi of u is u of I, so pi of f is f of I still. So this is just the f of I. Okay, and what's this? Again, this is just the suprema of these functions on the ith coordinate should be the same as the suprema of the fi values in the set of functions. So just okay, basically it says that and now we don't have to deal with projections anymore. So if this holds, then it means that if I have a chain of functions, then the supremum's functions ith coordinate should be computed as the supremum of the original function's ith coordinates. Now I can't recall whether we already proved this, but it holds in general, so I'm just taking a side note here, and I just make a separate statement out of this thing, and I will come back to that place later. So a statement is that if, and it will be quite useful even for proving the 2 to the z being CPO as well. So the statement says that if f is a subset of p to the I such that for each index I, the set. So if you just collect all the ith coordinates like this, has a supremum which is, for example, the case when f is a chain of functions and p is a CPO. Then these guys do have a supremum. Then the supremum of these functions exists, and actually it should be computed as follows. The ith coordinate of this function, of the supremum function, is exactly the supremum of these ith coordinates. Oops. The supremum f in f. So this statement basically says that if you just have to compute the supremum function, then this is exactly the function which gives you the result, which is the for each coordinate I, which is the supremum of the values those functions have. And actually, if the supremum does not exist, then neither exists the supremum function. Now this statement is quite cool, because if we just prove this, then this is fine. So this is exactly the same statement, because if f is a chain, then this supremum exists, because then fi is a chain, since if we have two elements, say fi and ji are members of this set, then since the original capital F was a chain of functions, then there are two cases: either f is smaller than or equal to g, or g is a lower bound of f. And in these cases we have fi being a lower bound of gi, and in this case we have gi being a lower bound of fi. So these two elements are comparable, which means that this is a chain, which means that the supremum of this chain exists. Yes. So yeah, that's exactly what we say. And okay, even if yeah, is a projection continuous, and if the supremum function exists, okay, so if the supremum function exists, then this supremum also exists. It doesn't really matter whether it's a chain or not. So yeah, this is exactly the same statement. If the supremum function exists, then this is the supremum function, and I just pulled this out into a separate statement, right? Okay. So let's do this. So first this guy, let's call this function to be f star. So let the function f star be defined as the function which takes the ith coordinate and outputs the supremum of these fi's. Okay, so the first thing is each member of f is smaller than or equal to f star, so basically it says that f star, this f star which we just constructed, is an upper bound for f. So for this end, let f be an arbitrary function from f. Again, we have to show that f is smaller than or equal to f star. Now these are functions. When are these two functions comparable in this direction? If they are comparable in this direction for each of the coordinates. So we have to show that for each I index, the f of I is smaller than or equal to f star of I. But this f star of I is just defined, and here we can apply the definition. And this is just the supremum of a set in F. And of course, this guy is an element of the set whose supremum is f star, meaning f star is of course at least as large as f of I, so f star is at least as large as f itself, so f star is actually an upper bound of f. That's fine. The second thing is that if it's a supremum, so if f has an upper bound, say g, then f star is a lower bound for g. So in order to be a supremum, we have to have what do we have? So it should be an upper bound, and it should be the least upper bound. So the least part is here. Oops. Eventually there will a secondary method will arrive. So okay, if f is smaller than or equal to g, then it means that for each f in f, we have f being smaller than or equal to g. Yeah, that's fine. Was this a comparison? Yeah, seconded. Was this a comparison of two functions, f and g? When do we say this? If this calls for each possible input. So for each f and for each I, we have fi at least as, so it's a lower bound for gi. Now we can just swap these two quantifiers, and we just say that for each I and for each f, we have fi lower bound for gi, and then here this means that the ith coordinates are below gi for each f. So for each I, we have this set f of I, f in f is, as a set, it's smaller than g of I. Now we can take the supremum of this set, which means that because if a set is smaller than something, then the supremum of this set is also a lower bound for the very same something, so it's the supremum of this set. We had this statement a while ago, and we are just using it again for each I. And this guy there is, if you just see this, is the same thing here, so it's f star of I. So for each I, we have that the f star of I is lower bound for gi, which is exactly the definition of f star being smaller than or equal to g, which is exactly what we had to show. Yeah, right. So it says that if I have a bunch of functions and I have to compute the supremum of these functions, then I should do this coordinate-wise, point-wise, taking the supremum, which already proves that projections are actually continuous. Now, before moving on, if we are on this topic of computing the supremum of functions, there is another statement which says that if P is a CPO and I is an index set, then P to the I is also CPO. Now that's quite important for our method because, of course, 2 is a CPO. All the chains have a supremum because, well, it's a finite poset. So in a finite poset, you only have finite chains. And the finite chain always have a maximum element, the largest element, I mean. And this largest element will be fine for the supremum. So since 2 is a CPO, so is 2 3Z. And this is one of our primary aims today. If you just check this, 2 3Z is a CPO. That's exactly what I wanted to show right now in order to the Tarski theorem to be applicable. So let's do this. If P is a CPO and I is an index set, then P3I is also a CPO. So let's try to prove this. Okay, so for this P3I being a CPO means that if I have a chain of functions, then the supremum exists. Okay, that's what I have to show. So let F, again, subset of P3I be a chain of functions. A chain of functions. We have to show that the supremum of F exists. Now, of course, it says that the previous statement says that if the set F to the I, F in F has a supremum. So let's check this. So now, for each I in I, if I just take this set F of I for each F in F, then this is also a chain. It's a chain since so if I just pick two elements, say if we have Fi and Gi are two elements of this set, then again, similar as before, if F is smaller than G, because originally F was a chain of functions, it's either F smaller than G or G smaller than I. So if F is the smaller guy, then Fi is a lower bound for Gi, otherwise it's the other way around. So it's, yeah, Gi is at most F of I. So they are comparable either way. So, and since it's a chain and this is a subset of the poset P, because it just contains values, it means that this supremum of these guys exists. Fi, F in F. So exists because P was a CPO. Now the previous statement says that if F is a set of functions such that this set has a supremum, yeah, that holds, then the supremum exists. Okay, which means that the supremum exists. Done. Cool. So if I have a CPO and I make the functions mapping to the CPO from earlier set, then I also get a CPO, which means that I'm already done with this. Now with the continuity of TP, I'm not finished yet, but I'm on the way because I've already shown that these guys, the UPIs, are continuous mappings, and I just have to take this finite conjunction of these things. In order to define a finite conjunction, I first will define a tupling operator. A tupling operator is the following. So basically I will have a bunch of functions computing separate values, and I'm just putting these values into one single vector. Let's say it's a vector. This construction of taking a number of values and just put them results, and just put them into a single vector, say, this is called target tupling. So that P and QB posets, say, I is some index set, I will index the vector with I, of course, the vector functions, and for each I, fi p to q be a function. Yeah, so I took a bunch of functions having the same type of input and having the same type of output. Then they're tupling, then they're, say, target tupling, and I will just write this in a separate color with a much readable font, target tupling. Okay, so where does a target tupling gets as input? A single p. Target tupling is the function. It's usually denoted by these angle brackets. So it's fi, I and I. Yeah, so that's it. It takes something from Q and outputs something which is a vector. So basically a function taking an index I and outputting a value. Okay, defined. Yes. Okay, so again, if I have this tupling of functions and I apply this on some point P, some x, I'll get a function. And how should I compute this function? I'm a vector. Well, I just have to tell what should stand on the ith coordinate on the output vector, and this should be the value of the ith function. Yeah, obviously. So it's basically, this is just saying that it's just, let's create the vector consisting of the results, and the ith element of this vector should be the result of the ith function. Of course, it doesn't need to be a finite thing, so that's why it's so abstract. Okay. The target tupling is interesting because for a closest body, I'll already have these separate values, up1, up2, up3, and so on. And in the first step, I just computed these values. Each of these were computed by a continuous function. And in the second step, I'm just putting all these results into one single vector. This vector will be finite for each close, because the closes have a finite body always. So the statement is the target tupling of continuous functions is continuous. Target tupling of continuous functions is also continuous. Okay, let's prove this. So what should I say? What should I prove? So the target tupling is a function getting a value from P and computing, say, vector Q3i, which means that proof let, say, X be a subset of P, be a non-empty chain, okay, so for the continuity definition, we need that for each non-empty chain having a supremum, the two operators can be swapped. So a non-empty chain with supremum, say X star, and we have to show that the tupling function, so if I apply the tupling function, tupled function on the supremum of the X values, then this is the same as taking the tupling function for each X in the set, in the chain, and then take the supremum of these guys. I should prove this. Yeah. Now, since I'm on the bottom of this page, I will just relocate this part. Or at least I will try to relocate this part. Yes, this part. So let's just move this. Okay, we have to show this. Now, what is this? Basically, I'm just applying a tupling function for an element. So let's just first check the types. So it's just tupling function applied to some point, which means that this is a member of Q3i, and this is of course also a member of Q3i. So these are basically vectors. So we just have to show that these coincide for each possible index I. So we have to show that the f of I, so it's the tupling function applied on the supremum, the viewed on the ith coordinate, is the same as, let's compute this function. Let's compute this function and let's view this on the ith coordinate. Okay. Now what's on the left hand side? Apply the tupled function on some point, and then let's see the ith coordinate. This is by definition of the tuple. This is just the fi of the supreme of X. That was the definition of tupling, how to compute tupling. And then, since fi is continuous, because the original statement said that if all the functions fi are continuous, then they're tupling, and so is their tupling. So this is basically first for the tupled f, and the second is because fi is continuous. Because fi being continuous, I can swap the application of fi and the supremum because X was a chain. So this is just the supremum of the fi of x's, x in x. Hopefully this is the same thing which will come out from the right hand side. So what's this? From the outside is just the ith coordinate of some function which is a supremum of some several functions. It doesn't really matter which functions at this point, but we know that if there is a supremum function and I have to evaluate the ith coordinate of that function, then for that I should just compute the supremum of all the values. This is which was actually proven today. So in order to compute the ith coordinate, the ith value of a supremum function can be done by just computing the ith coordinates of the functions in question and then take the h supremum. Yeah, so this is just the statement about this. The supreme function, how does it look like? And again, this guy here is just apply the template function on x and see what's on the ith coordinate. Oops, x in x. And this is the same as just apply fi on x for each x and check the result. So if you just see this guy and this guy are of course the same, which means that the tupling is indeed continuous. Okay. So if I compute the tuple of continuous functions, then I will get continuous function. Yeah, that's great. Now where we are, let's just get back to the definition of the TP function. Here, instead of just talking about the individual values, I am able now to just not the conjunction, but just create the vector up1, up2, up3, and so on, upn for each clause, and just like that. So without applying any operator. So basically, where I am now is just that the function so far which just gets an assignment and outputs a vector with the values of these variables in some order. The order is not really important. upn is continuous because this is a target tupling of projections. Projections are continuous and the target tupling preserves continuity. Yeah, great. Now next part is just to prove that the finite conjunctions, and this is important, the body of the clauses is always a finite thing. Here I will just prove this for a finite conjunction. So this next statement, so for any n integer n, the mapping, the function n-ary conjunction, so it's just 2 to the n to 2, and we are just taking x1, xn to their conjunction. This will be responsible for actually computing the left-hand side. Computing the body of a clause is continuous. Okay. So let's try to prove this again. N-ary conjunction is continuous. Proof. Again, if I'm having this function, then I have to get a chain from its input poset, which is 2 to the n. 2 to the n is just a shorthand for 2 to the 1, 2, 3, 4, n. So there are vectors having the first, second, fourth, and so on, nth element. So proof is let x be a subset of 2 to the n, so it's essential vectors, be a non-empty chain. Non-empty chain with the supremum, say x star, Okay. Now we have to show that the n reconjunction of the supremum of these values, of these vectors, is the same as just taking the supremum of the n conjunctions of these values. Now here these x's are just from assignments, actually n vectors, so x in x. So in a single x there is now n Boolean value. There are no n Boolean values. Okay. Now the very important thing here is that this is a finite set. This is finite, which means that if it has a chain inside, then the chain itself is finite. So since the chain is finite and it's a chain, so the elements are comparable, then there is a largest element amongst these guys, and that will be the supreme. So basically it's and if it's a chain, a finite chain can always be arranged as, so x is like x1, x2, blah blah blah, and x, let's say k, and xk will be x star, which is the supreme of x, right? So no matter how you construct a finite chain, if the elements are pairwise comparable, then there is an order, a strict order amongst them. Okay, so what is the type of these values? So the n conjunction outputs a single value, either 1 or 0. So I will just check when these sides evaluate to 1, right? So when does the conjunction of this thing evaluate to 1? Well, if and only if x star is 1, 1, 1, 1, which means that xk is the 1, 1, 1 vector. Yeah, that's right. This is the only case when the result is 1. Now on the right hand side, this guy is 1 if and only if, since it's a supremum, the supremum will be 1 if and only if there is a 1 within these elements, because each of these elements are either 0 or 1, and you can get to 1 only if there is a 1 inside the set. So it just says that if there exists somebody for which the n conjunction is actually 1, which means that actually the 1, 1, 1 should be a member of the set. But since the 1, 1, 1 element is itself the largest element of this whole poset, it will be the largest element of the chain as well. So and the largest element is just xk, so it means that again xk is the 1, 1, 1 element, because it can't be anything else than the last element, because this is the largest possible element in this set. And it seems that the two sides evaluate to 1 exactly in the very same case, which means that they evaluate to 0 in the other case, when it's not happening. Cool. Now, where are we? Now we are there. This guy here, taking a u and computing the vector of these values, is continuous. And from this, I can deduce that there is, say, x1, xn, or xn, okay, let it be n, to x1 and xn is also continuous. what I'm computing right now is a composition of these two functions. First, I get the u, apply a function, get this vector. Second, I get this vector and then I apply conjunction on this. So this is just chaining two functions. And we haven't shown that this also preserves continuity, but it does, and this is the next I will just try to use. And that will mean that for each clause, the evaluation of the body of the clause is a continuous function. So another statement is that if f p to q and g q to r, so in this case p is the poset of assignments, q is the poset of n-ary binary vectors, and r is the 2, so it's just 0, 1, are continuous functions, then so is their composition. Now, I think in this subject we use this notation G circle GF, which is a P to R function. Okay, so you can define the function if you wish. So G circle F on X should be computed as first compute f of X and then compute G on the result. Yeah. Now that's the statement that if you just chain two continuous functions together, then the result will be also a continuous function. Let's prove this. Again, this is a function. I want to show that this is a continuous function. These are the types, so I have to start from a chain in P because it's the input. This is the input poset. So let X be a subset of P, be an empty chain, as always, and X star be the supremum of X. Okay, we have to show that if I just apply G circle F on the supremum of X, sorry for the advertisement, on the supremum of X, this will be the same result as applying this G circle F on every element of the chain and then take the supremum of these values. So we have to show this. Now let's start from, okay, now for a while there won't be any advertisements, but sooner or later there will be again. Now let's just start with extracting the definition. So G circle F of X is just G applied on the F of X, X in X. Okay, and this guy here is just G applied on F applied on the supremum of X. Here F is continuous, so I can start with just this part. Since F is continuous, X is a chain, non-empty, and has a supremum, I can just rewrite it, and I will just rewrite that part. So it's just the G of the supremum of the F's of X for each X. Now, since G is continuous and G is applied on a supremum, I am able to swap these two operators if the inside of this supremum is a chain. But this is again a chain because if X is smaller than Y, then f of x is smaller than f of y again. So if you just pick several elements, two elements from this set, say f of x and f of y, since originally x and y were members of a chain x, then they are comparable. If x is smaller than y, then f of x is smaller than f of y, and it's the other way around if it's not, because f is continuous, so f is monotone. Yeah, that's important here. So this is a chain, which means that I can swap these two operators, and this is just the supremum of the members of these guys. Yep. And this is the same again. So composition preserves continuity, which means that right now I'm at the point where I'm almost complete, because no matter how I just pick variables, I can compute take the u and just compute the up1 and upn. This guy here is continuous. Okay. Now, how is the TP function looks like? There is a part resembling this. Yeah, that's it. So this here, and then there is a supremum operator on these functions. Okay, so we have a bunch of continuous functions. For each clause we have a continuous function, and some of these continuous functions are just taken to the supreme, and then we will get this here. This is the current name. It's almost done, So for this, of course, we'll have a separate statement, but maybe here. So the statement is that if f is a set of continuous functions, and the supremum of f exists, of course the supremum of that formally exists because the output is just either 0 or 1, so it's, yeah, you can take the supremum of that thing, then this continues. Okay, let's prove this. I should just emphasize that it's P to Q. In the TP case, P is the poset of all assignments, and Q is the set of all bits. So it's just a poset too. It's a proof. So that X, again, for continuity, I'm always taking the non-empty chain. A non-empty chain. And let X star be just the supremum of X. We have to show that if I apply the supremum function on the supremum set, on the supremum of the set, that's the same as if I apply this supremum function on all the possible values and then take supremum of these results. Now the supremum function we also already know that the supremum function is the same as just compute the values and take their supremum. So if it exists, then it has to be the following. So it's just, let's take the supremum of all the functions on the supremum of x belonging to f, to capital F. Now here f was a set of continuous functions, so each of these small x's are continuous, which means, and x is an unempty chain having a supremum, so I can swap here the f and the supremum because of the continuity of f. So this is just the supremum of another supremum of the f of x's, and here x in x is the inner variable, and there f of f is the outer variable. Now as this is a supremum of supremum, and this is exactly the type of supremum nesting which we already proved that this is the same as the flattened version of the supremum taking, so it's just the same as a large supremum of all the values f of x, for which f is a function from the set and x is a member of the set. So this was just along the lines that taking row-wise supremum and then the supremum of the row supremes is just the same as taking the whole Taylor's supreme at once. This is just the application of the statement. So it's just nested. Now on the right hand side, what we do have is just the supremum of f applied on x. Now again, we have this statement about the supremum function. How to compute the supremum function? Well, you just have to compute the f of x's and take the supremum of that. So we just take the supremum of the f of x's for the f, and then the outermost x of x, it doesn't change. So as you can see that in this and in this, the order of these, let's say, loops is different, because in the first part f was the outer variable and x was the inner variable, and here in the right hand side is the other way around. But still you can just flatten this whole thing, and this will be the same as the supremum of all the values f of x for f in f and x in x, which is great because these are the same, right? So you just have to iterate all the functions and all the values, and that will be the result. Now that's good. So if f is a set of continuous functions and their supremum exists, then the supremum is also a continuous function, which means that for each q, and moving back to the TP function, for each fixed q, this expression is a continuous function, which is great because the whole TPU function is just a target tupling of such functions. For each q, I have this function, and the result of TPQ is a single vector, which is just the target tupling of these functions taken for each q. So since I have this, and I already know that the target tupling preserves continuity, I get that TPU is also a continuous function. Great. Which means that we are done with the semantics of logic programs, because if we accept the experts, well, golden rule that a canonical model should be a minimal one, then these theorems say that there is exactly one possible choice, because a model is a prefixed point of this function Tp. A minimal prefixed point is needed, but for the prefixed points, well, applying the Tarski Fixed Point Theorem, we get that there is exactly one minimal prefixed point. This happens to be a fixed point as well. This happens to be the least fixed point as well, and it can be computed by just iterating the TP function from the constant 0 assignment, and just take the supreme of these assignments, variable assignments. The supremum will exist, and it will be the unique least prefixed point of the function TP. So this should be the canonical model of logic program. So this concludes the part of classical logic programs, of negation of free logic programs, and in the next part of the course we will just extend these results to programs containing negation as well, but that's in another video. Till then, bye bye.